Before we start a simple beam problem, I just want to remind everyone that with the sign convention when doing shear and bending moment diagrams. So if you have a beam and you slice it and you look this way, if the shear is going up, it's positive. If you do your method of, I should say if you do a method of sections, okay, method of sections here, method of sections here on this beam. If your shear on this side is going up, it's positive. If your shear on this side is going down, it's positive. Now what does that mean on this side? So if you slice it on this side and you have material here and no material here, you're looking to the right. Well, up is positive. But if you do the opposite on the other side and it's going down, it's still positive. And the same with, and I think I said this in class, an M that causes the beam to smile is positive, and an internal M that causes the beam to frown is negative. So now let's start the problem. Today we're just going to look at this simple problem. Strength of materials. You've got a single point load of 2,000 newtons located at the midpoint of a beam. You have point A and point B. This is a pin, this is a roller, so you can't have a moment response reaction at the end. And here we have a free body diagram where we have reaction in A, reaction in B, and you have 2,000 newtons at the center. So recall these are the relationships, and I haven't derived them just yet, but the dV by dx, or the slope of the shear curve, is equal to the negative W. I know in class I haven't been writing it as negative W, but I have said we consider a distributed load pointing downwards to be negative. And then we have the slope of the moment curve is equal to the value of shear at that point, the exact same point in the curve. So what do we do first when we solve this? Here is one we solve for reactions, right? So reactions. Okay, so if we take the sigma moment about A equals 0, remember this is positive, then we're going to get moments about A, so we're going to get RB times 10 meters is positive, RB 10 meters, that's a positive. The 2,000 newtons pushes this way, so it's going to be negative, right? So minus 2,000 newtons times 5 meters. So solving for RB, we get RB is equal to 1/2 of 1,000, or 2,000 equals 1,000 newtons. Okay, so RB is equal to 1,000 newtons. This is 1,000, this is negative 2,000, then RA must be 1,000 newtons. Okay, so for the shear curve, the first thing we want to do is just draw the method of sections right there, or use the method of sections right there. Draw an FBD, another one. FBD. So we're going to have 1,000 newtons here. And we're going to have some shear value here, V, and we're going to have some unknown M. So your sigma Fy, if I call this your method of sections 1, okay, so you're going to have sigma Fy equals negative V plus 1,000 newtons. V is equal to 1,000 newtons. So when you draw your shear and bending moment diagram right here, actually all the way across until you hit this point load, your shear value is going to be 1,000 newtons. So let's do an MOS2, method of sections 2 over here. 2. So this was, sorry, MOS1 here. MS1. Going to go MOS2. So we're going to get, if I just scroll down here for a second, we're going to get 1,000 newtons And this is the positive direction for shear according to our convention. So it's the opposite of when you slice and look this way. Now we're slicing and looking this way. So we do sigma F y equals 0 equals V plus 1,000. So V is equal to negative 1,000 newtons. So your shear diagram will have these two, a shear value of 1,000 going over here. That's this value right here. And then once you hit the 2,000, it flips to negative 1,000. So that's it's a pretty simple shear and bending moment diagram. So now what I'm going to do is I'm just going to turn off this layer, turn on this layer, make it active. I'm just going to go back up here and I'm going to, let's just start our shear and bending moment. Not the straightest lines in the world, but I think you get the point. Okay, so remember, make sure I remember here, that the shear in your method of section 1 here is 1,000. And once you pass here, it goes to negative 1,000 here. Okay, so this is V. Let's do this here. This is V. Okay, V and V. So positive 1,000 here, negative 1,000 here. Let me turn off that layer. Make that layer active. So positive 1,000 here. Goes until it hits the negative 2,000 load, and then it drops to negative 1,000, and it goes to negative 1,000 here. So pretty simple shear and bending moment diagram. Okay, I guess it's in newtons. This will be shear. So now we want to look at, now that we've completed that, we're going to do our moment. And just to back up for 1 second, you know it's 1,000 here, you know you had a 2,000 pound Newton load, and then it drops to 1,000 here. So that's where you can draw this straight line here. I could do a method of sections where I section the beam here, draw a dotted line there, and I have my 1,000 up at the end, my 2,000 down here. You'll get the same value, negative 1,000, because of the sign convention of shear. But really, if you just start at the end where you've got your 1,000 and just do your method of sections, as I did, you find out it's negative 1,000. So 1,000, negative 1,000, and they meet at the 2,000 Newton point load. So what relationship are we going to use to figure out our moment diagram? Okay, so let's turn this layer off. So remember these relationships up here. So dV by dx equals negative omega. So, and that's your distributed load. So distributed load, in this case, is 0. So the slope of your curves, your shear curves, should be 0. And that's what we have here, right? This slope is 0, this slope is 0. But what other relationship did we show here that we can use? Well, that's your dm by dx equals v. Now, let's just go back and think about this for a second. Make this active. I'm just going to write over here, dm by dx equals v. And if you know integral calculus, really what this changes into is delta m, if you bring your dx up over here and integrate, is equal to the integral of v dx. Well, this is just equals the area under shear curve. Okay, so there's two ways to look at it. You can look as your V here as your slope. Well, your slope over, it's a 10 meter beam over 5 meters, should get you to dm by dx equals V. So a slope of 1,000 over 5 meters should get you to 5,000 Newton meters, right? So let's just draw this out again. So dm by dx, so the slope of your end curve is equal to the value of shear, where the shear is constant at 1,000. So that means your slope here is 1,000. So 1,000 over 5 meters equals 5,000 newtons, right? Also, the area under the curve is 1,000 times 5 meters, right? Shear area equals 1,000 newtons. 5 meters equals 5,000 Newton dot meter. Well, that's what we're at here based on the slope. So we're getting the same answer. Okay, well, what about this here? Well, this is negative area, right? So it's negative 1,000 times 5 is negative 5,000. So now we come down negative 5,000. Also, dm by dx equals v. Well, it's negative 1,000 slope. So negative 1,000 slope over 5 meters gives you negative 5,000 Newton meters. So now you're back down to 0, which makes sense because you know, based on this here, pin and roller, you have a moment of 0 at the ends, right? Well, what do we have? We have a moment of 0. So this is basically how you would solve this very simple point load shear and bending moment diagram. So this, just to summarize, 2,000 newtons down at the midpoint results in a 1,000 newtons reaction on each end. Let me just write 1,000 here. 1,000 newtons. So those two reactions combined with the load result in your shear and bending moment curve looking at 1,000, negative 1,000, and then you can use these two relationships here, dm by dx equals v, or delta m equals the area under the shear curve, v, or integral of v dx. And you can see you end up with these shear and bending moment diagrams. That's it. I will work on some more shear and bending moment problem solved. Cheers.